Okay, so the way this works is I don't have a specific agenda. I am going to share my screen and use a whiteboard just like I do in class. But I don't have specific questions or anything of that nature pre-prepared. So you're going to need to ask specific questions, or you can put them in the chat if you would rather, if you don't want to speak. But anyhow, that's how these study sessions work. Is I don't have a specific plan. I'm going to answer questions. So let me get the screen shared. And okie dokie. So again, you'll just need to ask your question. You can either unmute yourself and do it vocally, or if you'd rather type it in the chat, you can. And I will do my best to answer.
Okay, I'm super confused on the z-effective calculation still.
Okay, so when it comes to z-effective, the very first thing you need to look at is whether it is an S and P orbital or whether it is a D and F orbital. Because we treat SP and DF slightly differently. With SP, it is 0.35 if the electron is in the same shell. Keep in mind the shell is represented by the numerical value that precedes the letter in the electron configuration. It is 0.85 if it is in the N-1 shell, or in other words, the shell that came right before it. And it is 1 if it's in the N-2 or lower shells. Now with D and F, it is 0.35 again if it's in the same shell, but it is 1 if it's in N-1 or lower. So that's the difference with D and F compared to S and P, is that we pretty much jump straight to the 1. So if I had z-effective for, say, calcium, the first thing I would do is I would write out the electron configuration for calcium. And then you can either write it out in this format, or the other thing that also can be useful is instead writing it out in the box diagram. And let's say I am wanting the z-effective for this electron in blue. I could have picked that electron, or I could have picked the other electron. It really wouldn't have mattered. Now, what we're looking at is the shell. Our shell for our electron is equal to 4, because that is the number that we see. So that's the shell of our electron. Now, what that means is, again, we're going to go up here. The same shell would be 0.35. So anything in the shell of 4 would be a 0.35. So we have 1 electron in the shell of 4. So that would be the 1 times the 0.35. The next thing we're looking at is the n minus 1. Well, if it's n minus, why isn't it writing? If it's n minus 1, well, that would be 4 minus 1 is equal to the 3. So anything in the 3s would get the 0.85. So there's 8 electrons in the 3. And then for the last one, we're looking at n minus 2. Well, again, that would be 4 minus 2 or lower. So anything in the 2 or lower is going to be a 1. So all of these are in 2 and lower. So we would have 10 electrons times the 1. And that would be from these would be the values that we would be subtracting out from our atomic number. Well, calcium is element number 20, so that's its atomic number. So our Z effective is going to equal the 20 minus the shielding for each of these divisions. And that's basically what we're looking at, is how does the 1 electron in the 4s shield from the one we're wanting to look at? How do the electrons that are in the third shell shield the electron we're studying? And how do the electrons in the anything lower shield? And so once you do that, you would simply do the calculation to get the Z effective. So it's literally going to be a matter of following these rules up here and knowing what shell you're starting with. Does that answer your question? And because I couldn't see who spoke to me, I'm going to have to be very generalized. Does that answer your question?
Yes, ma'am.
Does it make sense now, or do you need another example?
No, that makes more sense.
Okay. So that's all there is following rules.
Would you write the, or calculate, go over the Z effective for PB4 plus? Because I got a different answer than what was on the key, and I could not understand why.
Well, I could have screwed up is why, but yes, I can do that.
Okay.
I mean, I'm not above screwing up at times. So, okay. So with PB, the very first thing I'm going to do is PB, which is going to take a little bit. So give me a little bit of time here. And I'm doing everything from memory because I, for some reason, don't have a periodic table home, but that's okay. I think I can do most of it. I'm not mistaken, let me make sure. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p2. If I'm not mistaken, this is the electron configuration of lead.
That's what I got too.
Now, okay. Now, if I am talking about lead 4+, that means I have to remove electrons. So the electrons that will go away will be the 6s2 and the 6p's. And the reason is those are the ones in the highest shells. So now to get my lead is element 82, I believe it is.
Yes.
So Z effective is going to equal 82 minus. So what we're going with again are these rules that are up here. So the question is it in the same shell or is it in a lower shell? Well, since we got rid of all of the 6s, we don't have anything. So our shell for lead is 6. So N-1 would be 5. So the 5Ds here would be a 1 because they're already N-1. But also these 4Fs would be a 1 because it's N-1 or lower. So all of these would be a 1. And right now I'm doing the D's and F's, so let me make note of that. So any D and F that is 5 or less would be a 1. Any D or F less than 5 is going to be a 1. Now for our S and P, N-1 is equal to 5 again. So anything in S and P that's 5 is a 0.85. And anything that is in N-2 or lower, which would be 4, so 4 or lower, is going to be a 1. So this would be a 1, and all of this will be a 1. So let's see here. Let me move this down a little. So my Z effective is going to equal 82 minus, let's see. So I would have 14, even you could do it by each grouping if you want. 14 times 1 plus 10 times 1 plus 6 times 0.85 plus 10 times 1 plus 2 times 0.85 plus, and I'm going to do the rest of these because they're all 1. So 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So another 36 times 1. So I'm going to have to do this way. Okay, that would be 82 minus 14 minus 10 minus 6 times 0.85 minus 10 minus 2 times 0.85 minus 36. And when I get this, I got 5.20 if I keyed it into my phone correctly.
Okay, that makes sense. What I did was I said that 5 became the highest shell since there were no electrons anymore in the 6, but I guess that's where I went wrong. So it's still
right.
6.
6 is still the shell. It's just the, because that's what lead was. Yes, we removed them, but that's still what lead was.
Okay, that makes sense. Thank you.
Okay, you're welcome. So I had a couple of questions in the chat. So let me go pull up the chat so I can see it again. Okay, could you outline exactly what we need to know for this test? I know it's quantum mechanics, electron configurations, ions, atomic size, and electron affinity, but I'm not sure as far as naming what we need to know. Okay, so first thing is for the most part, it is outlined on Blackboard, but as far as naming is concerned, you need to be prepared to give the name or to give the formula of the metal cations who always have the same charge, the metal cations whose charge can vary, the elemental anions, and the polyatomic ions that are listed. It was what I think was page 4 of that packet I handed out, which is the one that had the periodic table on the right-hand side. So it started with borate, carbonate, and went over towards the halogens. So those are the ions you have to be prepared to give either the name if I give you the formula, or the formula if I give you the name. Otherwise, there is no naming on this test. It'll come up on the next test. Does that answer your question about that, Lana? Okay. Before I move on to your other question about the radial and angular nodes, let me go back, and David asked, why would it be 1? I need you to be more clear on why it would be 1. Which part? I can't see faces, so okay, the 4F, why would it be 1? Because of the definitions up here for DNF, only if it's in the exact same shell is it 0.35. If it's anything below the original shell, so N-1 or lower, it's a 1. So since our shell was 6, then 6 minus, so only if it had been in the 6 Ds or 6 Fs would it have been 0.35. Everything else is going to be considered lower because the principal quantum number is represented by the letter, it's represented by the number in front of the letter. So you typed in 4F in the chat. The 4 is the N. So 6 minus 1 is 5. So 5, 4, 3, 2, and 1 in the D's and F's would all be a 1. Does that answer your question about that, David? Okay. And okay, that also answered Aaron's question. So that's good. So now I'm going to go back up to Lana's other question about what if I could go over how to calculate radial and angular nodes. Okay. So before I get into doing the calculation piece for angular and radial nodes, the first thing you've got to be able to do is identify the shell and subshell. So let's talk about that first before we move on to doing the other. And what I'm going to wind up doing is I'm going to wind up still sharing my screen, but I'm going to go try to find the homework document so that I can illustrate it better than I can with just simple drawings. Okay, so the very first thing is you have your S, your P, your D, and I can't draw the F. Now, what you have to remember is where the S's begin. Your very first S comes in shell number 1. Your very first P comes in shell number 2. And your very first D comes in shell number 3. We need to keep this in mind in order to help us identify the shell and the subshell so we know how to calculate our angular and radial nodes. Once we've identified the shell and the subshell, then what we're going to do is we're going to use the formulas where the total node is n minus 1, where again, n is the shell. The radial nodes will follow the formula n minus 1 minus L, where again, n is equal to the shell and L is equal to the subshell. And you have to remember that when we're talking about quantum numbers, this S here for an L value is equal to 0. A P for the L value is equal to 1. And a D for the L value is equal to 2. And if we had an F, it would be 3. So when we're looking at this, it is this L number that we're subtracting. And then your angular nodes is equal to the total nodes minus the radial nodes. So that is the formulas we're going to need. Now I'm going to go in and try to demonstrate all of this using the homework. So if you'll give me a second, I'm going to pull it up. Let me think how I'm going to get there. There. And that would be 7 or 8, probably. Let's see. No. Sorry, it's taken me a minute. There it is. Orbital and nodes. Okay, so let's see, I'll see if I can write on it. Nope, it's not gonna let me. Crumb. Okay, so sorry, it's taken me a minute. Okay, so with this very first one, get back. With this very first one, if you look at that inner circle, that's, first of all, it's a circle. That means that it has to be a S. And S's always start in 1. So that inner circle has to be the 1S, and then we count out. So this is, so 1S, and the next circle would be 2S. So this is a 2S. The next one, because I'm not being able to use my pencil, so I really want to go back to the other screen as soon as I can. With this next one, first of all, it looks like a clover leaf. Since it looks like a clover leaf, then we know that it has to be a D. Well, D's start in 3, so that innermost D is a 3D. And then we simply count out red, so we could count the red. On the right-hand side, it would be 3D, 4D, 5D. And that my pencil's now working, so I'll just continue. So on this next one, this is a dumbbell shape. Because it is a dumbbell shape, it means it's a P. Well, that means that this inner area is 2P because that's where the P's begin. So this is a 2 and this is a 3. So we're talking about the 3P. And I said this was the 3D here. So this is the 4D and this is the 5D. So you have to know where the subshell begins to know what you're looking at. On the next page, this is a D because it's a clover leaf, but notice, and the 3D is the very first one. Since this is the first one, it has to simply be a 3D. That's all its options are. The next one is a circle. Well, circles are S's. S's begin at 1. So this very inside is the 1S. And then we simply count out the next one's 2S, the next one's 3S. So this is a 3S that we're talking about. The next one, it's a clover leaf. Clover leaves are D. D's start at 3. So this inside one has to be the 3D, and then this next one would be the 4D. So this is the 4D. That is how you go about figuring out what it is. You start with, this is an S, where does S's begin? And that is what the innermost piece will be, and then you simply count outwards. So that gives us our orbital. Now our total note is going to be n-1, where n is represented here. So it's equal to 5 minus 1. So the total notes have to be 4. The radial nodes is n minus 1 minus L. So n, again, is the 5 minus 1. And then our L is represented by the D. And anytime we have a D, that means L is equal to 2. So minus 2. 5 minus 1 is 4, minus 2 is 2. So the total radial nodes is 2. To get the angular nodes, you subtract the total nodes minus the radial nodes. So in other words, 4 minus 2, that means it's equal to 2 as well. So for the 5D, you would have 4 total nodes, 2 of which would be radial and 2 of which would be angular. I forgot who asked the question, but does that answer that question for you? And it said, yes, it does. Okay. Anybody else have a question about how to figure out the orbital that we're talking about? Because that's where it all begins, is figuring out what orbital you're dealing with.
I had a question on the second page, if you are able to go, where you have the 4D example.
Mm-hmm.
That's the right answer, right? Because I know on the key for the optional, it said that it was 3D.
Well, this first one was a 3D, but then the third one should have been 4D.
It may have been. Let me just, I can look real quick. Yeah, the first one says 3D and then the 3S, but that one says also 3D. So I was just making sure that it was 4D.
Oh, no, it should have been a 4D. I was doing them rather rapidly. So
okay,
this
I was just making sure that I was doing it right and not doing something wrong.
No, that's my fault. I'm sorry.
Oh, no, it's okay.
Any other questions about that piece? Okay, I'm trying to go in order and not forget any. So the question I was asked, do we have to know what axis the nodes are on and how to draw them? Mohammed, are you asking me, do you need to know whether it's the DZ squared, the DXY or X squared, or the DXY or something like that? Is that what you're asking me? Okay. You do not need to know that piece of information. You just need to know whether it's a D, an F, a P, or an S. You don't need to be able to identify which axis it's on. Okay, let's see. I have one asking for the review and showing example of the Rydberg-Balmer equation. Okay, let me go back to here then. And we'll do the Rydberg-Balmer. So let's say, and I think this is actually the example on the sample test. The very first thing you need to do is be able to recognize words that will help you to figure out what equation you need to use when. So if I see a question that's asking me about energy level, that means that I am going to want to use the Rydberg-Balmer. But if I see a question that asks me simply for energy, then I want to use E equals H times the frequency, or E equals HC over lambda. And if I'm asked a question that is a conversion between wavelength and frequency, then that's when I would go into C is equal to the wavelength times the frequency. So there's keywords, in other words, that will help you. The next type of keyword that will help you is if I see the word visible light, then N sub F has to equal 2. If I see the word infrared light or infrared radiation or something like that, then I'm talking an N sub F of equal to 3. And if I see ultraviolet light or UV light, then I'm talking N sub F is equal to 1. So in other words, understanding keywords will help you to figure out what equation to use and what the N sub F is. So I believe on the example exam, I said that I gave you a wavelength of 656 nanometers, and I asked for, and it said visible light, so I caught on to that. And the other thing that I saw in there was the word energy level. So the very first thing, the very first one I needed is going to be 1 over the wavelength is equal to R times 1 over N sub F squared minus 1 over N sub I squared. And we were given the wavelength that was 656 nanometers. And because I said visible light, that meant that the N sub F had to equal 2. And then R, I do give you the equation and I do give you this constant, so you don't have to memorize them. R is 1.097 times 10 to the minus 2 per nanometer. Okay, so because I gave you R in nanometers, it's okay to leave your wavelength in nanometers. So 1 over 656 nanometers will equal 1.097 times 10 to the minus 2 per nanometer times 1 over 2 squared minus 1 over N sub I squared. And ultimately, we're solving for N sub I. So let me get back to my calculator on my phone. So I simplify things just to make my life a little easier. 1 divided by, let me double check that. 1 divided by 656 is 0.001524 per nanometer. That's equal to the 1.097 times 10 to the minus 2 per nanometer times, well, 1 over 2 squared is 4. 1 over 4 is 0.25 minus 1 over N sub I squared. I then divide, so this was just simplifying everything. Then what I'm going to do is I'm going to divide both sides by the 1.097 times 10 to the minus 2. So basically that's going to cancel out the 1.097 times 10 to the minus 2 on the right-hand side, and the left-hand side becomes, well, let me do it again because I think I screwed up. That becomes 0.13896, and the units go away at this point is equal to the 0.25 minus 1 over n sub I squared. The next step, I'm going to subtract 0.25 from both sides. So it goes away on the left-hand side and it becomes a negative 0.11104 on the left-hand side, and that is equal to a negative 1 over n sub I squared. I then multiply by a negative 1. So it becomes 0.11104 is equal to 1 over n sub I squared. I then take the inverse, which again is going to either be represented by 1 over x or x minus 1 on your calculator, depending upon what it is. And what I wind up getting is 9 is equal to n sub I squared. And then we take the square root of both sides and you get n sub I is equal to 3. So what this is saying is that the electron fell from n equals 3 to n equals 2 to give off to give light of 656 nanometers. So that's the process of doing Rydberg-Balmer. Now, if I asked you for the energy, which I think is the next piece, again, I see energy this time, not energy level. I see energy, and I automatically want to go to E equals HC over lambda. I will give you the equation, and I do give you the constants. Now, the most common mistake, and it occurred on the last test too, is folks did not pay attention to their units. And so our wavelength we were given is 656 nanometers. You have to pay attention to the unit. The units are not the same. We have meters in our speed of light and we have nanometers in our other. So you've got to change the nanometers into meters before you can complete this calculation. And to do so, you're going to multiply 1 times 10 to the minus 9 meters is equal to 1 nanometer. And this comes out to be 6.56 times 10 to the 7, or negative 7 meters. Once you have that, this equation should be a plug and chug type of equation, except you do have to pay attention to your, if you're not using the EE key, you have to pay attention to the fact that you have to have all of your parentheses since you have so many pieces in scientific notation. And so, and I don't know, this is going to come out to times 10 to the minus 19 because it is in, it is visible light, and visible light will always be at 10 to the minus 19. So 6.626 E34 negative times 3 E8 divide 6.56 E7. This comes out to be 3.03 times 10 to the minus 19. For the last one, I think I said to convert between wavelength and frequency, so we're going to do so using the speed of light. The speed of light is 3 times 10 to the 8 meters per second. So you're going to need your wavelength in meters. which we determined was 6.56 times 10 to the minus 7 meters. So C divided by the wavelength is equal to the frequency, 3 times 10 to the 8 meters per second, divided by the 6.56 times 10 to the minus 7 meters is going to give us our frequency. And I know that this is going to be 10 to the 14 because, again, I'm dealing with visible light. So let me do that one now. And it comes out to be 4.57 times 10 to the 14. Okay, now let me go back so I can see all of your content, comments, and questions. Okay, so where am I at? Madeline, does that answer your question? Okay. So again, the key to it, folks, is really knowing this piece of information. There's keywords that will help you along the way in solving the problems. Okay. For the 3S, Mohammed, yes, you should have had 3 circles. One would be on the inside, which was probably blue. And then the next one was probably a different color. And then the third one was probably blue again. I just don't remember the exact orbital diagram because I don't have it in front of me. But yes, that's what it should have been with the 3S. And that was an answer to Muhammad's question from when we were doing orbitals. Okay, so the next thing I was on this list is naming of ions. Oops, didn't want to do that. Okay. So there are certain questions that I ask myself when I see a metal. The question I ask myself is it group 1, group 2, silver, zinc, cadmium, aluminum, gallium, or indium? From there, if I answer yes, then I'm going to name the metal and attach the word ion. If I say no, then I'm going to name the metal, give charge as a Roman numeral, and that's sufficient for a metal that's not one of those. Now, the reason this works is because these always have the same charge. As an ion. Whereas the others, the charge varies. So that's the reason we have to ask those questions. if it's group 1, group 2, silver, zinc, cadmium, aluminum, gallium, or indium, their charges are always the same. The charges are a +1 for group 1, a +2 for group 2, a +1 for silver, +2 for zinc and cadmium, and +3 for aluminum, gallium, and indium. They're always those charges. So if I say I have magnesium ion, magnesium is in group 2, and because I added the word ion to it, it means that it's Mg2+. So that is the naming of a metal. For your nonmetals and metalloids, to name them, you replace the ending of the element with the letters I, D, E. So for instance, fluorine is the neutral atom of fluorine, whereas fluoride is the ion of fluorine, so it's a -1 charge. Oxygen is the neutral atom of oxygen, whereas oxide would be the negative ion of oxygen, which is a -2 charge. So basically we replace the endings with IDE. And unfortunately there's, other than in the halogens, I can't just say what you replace. In the halogens, you replace the INE with IDE, but with the others, you're just gonna have to get used to what you replace. Now for the charges, if I say I have nitride, because it's in group 15, it's going to be a -3. Group 6, if I say I have selenide, because it's in group 16, it is going to be a -2. And if I say I have bromide, whoops, that's supposed to be group 16, group 17, that means that it's going to be a -1. So basically for figuring out the charge on the nonmetal, it depends upon what group it's in. Okay. Now, one of the reasons that I emphasize the letters IDE so much in class is because other than 5 polyatomic ions, your polyatomics mostly, or I should say polyatomic anions, mostly end in -ate or -ite. And it is because of the last 3 letters that we have the ability to differentiate. Is it again, there's always some exceptions. There's 5 exceptions to what I'm saying. But in general, the ending tells us whether we're dealing with an anion of an element or a polyatomic ion. Now, the difference from -ate to -ite in families of 2 is 1 oxygen. Technically, that's true for the family of 4 too, but family of 4s have a little bit more. Now, the reason this, so one of the things I mentioned on Friday that will be useful is if you can remember phosphorus's polyatomics, and you can remember sulfur's polyatomics, and you can remember chlorine's polyatomics, then you know all of the polyatomics below those elements as well, because they behave exactly the same. If you compare phosphorus and arsenic, for instance, you're going to see that phosphate is a 4 oxygen 3 minus charge, and arsenate is also a 4 oxygen 3 minus charge. So they're identical except the starting element. And to go from the 8 to the ite, if you know phosphite is PO3 3 minus, then you know arsenite also, because it will also be 3 oxygens and a 3 minus charge. So you really only have to know the polyatomics for row 1 and for period 2 and period 3, because all of the polyatomics from period 3 down that you have to know for tomorrow behave the same. Did that answer your question, Haley, or do I need to go into greater detail? Trying to keep up. Okay. Let me think. The next question I had is how can I go over how ion charge affects size? So on the Z effective homework, which I don't know the numbers right off the top of my head, but you would see on the Z effective homework, I did PB, PB2 plus, and PB, PB4 plus. And what you would have noticed is that the Z effective increased from in order of lead to lead 2 plus to PB4 plus. Because the effective increases, size decreases. So in other words, as your element becomes more positively charged, the size is going to decrease. Now, as far as going the other way, you could actually do chlorine and you could do like oxygen. So let's just see from a Z effective perspective, oxygen, O minus and O2 minus. So if I did oxygen from a Z effective, I would, if I'm looking at, let me go in and actually fix this a little bit. If I'm looking at this one here and I do the Z effective, well, Z effective is going to equal, oxygen is element number 8, so that's its atomic number, and we're going to have to do this, so this is 2p. Because all of these are in the same shell, that's a 0.35 for them, and because this is in the N-1, that means that it's going to be a 0.85 for those. So we have 1, 2, 3, 4, 5. We have 5 times 0.35, plus we have 2 times 0.85. So that would be 4.55 if I calculated it correctly using my phone. Now, if we make O minus, now we're talking about this electron here. So our Z effective, when we start doing this, is going to be, again, these are all in the same shell. So our Z effective is going to equal 8 minus. Now we have 6 electrons in that same shell, plus the 2 in the previous shell. So this Z effective is going to be oops, I messed up. I keep messing up on my calculations, sorry. I believe it comes out to be 4.2 if I did the calculation correctly. So what you're seeing is, and if we did O2 minus, we'd see the same thing. So in other words, what you see is O to O minus to O2 minus. As far as the Z effective, it decreases this direction. And because Z effective decreases, size increases. So there's a direct correlation between the Z effective and the size is the key. Now, just so basically what this boils down to is if you have an isoelectronic series, a +3 would be smaller than a +2, would be smaller than a +1, would be smaller than a neutral, which would be smaller than a -1, which would be smaller than a -2, which would be smaller than a -3. And it really all does come down to that Z effective and how it's impacted. So let me go back, trying to keep up, sorry. Did that answer your question, Lana? Okay. Now for Amaya, is there chemical formula problems on this exam? The only formulas you have to know as far as being able to come up with names to formulas are the ions of the elements, all of them, whether they have a metal whose charge is constant, a metal whose charge varies, or an anion of an element. You have to know how to name or come up with a formula of all of the ions of the elements. And then you need to know the polyatomics on that one sheet that's got like a half a periodic table. It starts with borate, and then you get carbonate, and then you got peroxide and something. Well, no, you get nitrate and nitrite. Those you have to know, but you do not need to know how to develop the names of ionic compounds as of yet. Does that answer your question, Amaya? Okay. In answer to your question, Mohammed, about Heisenberg uncertainty principle and other stuff, the answer is no. If I didn't ask it on if I haven't asked a question similar to it on a homework, or you don't see something similar to it on that one exam, other than, so basically what I guess I'm trying to say is Heisenberg uncertainty principle will not be on the exam. Neither will the Schrodinger equation, because all that was just leading into us understanding the quantum numbers. Does that answer your question, Mohammed? Okay. Jacob, have we already gone over quantum numbers? The question is, in what regard? We've gone over them from an orbital perspective, but not quantum numbers directly. And I can go over quantum numbers directly. Okay, so quantum numbers are always N, L, M sub L, M sub S. It's always in that order. N will always be a whole number from starting at 1. So it'll be a 1, a 2, a 3, and so on. L will always be 0 to N minus 1 on a number line. So in other words, you won't ever have anything below 0, but it can go up higher depending upon what the N value was. M sub L is everything from a negative L to a plus L on a number line. So here's where you will have some negative numbers. You do not have negative numbers until you get to here. Oops, except I can't do anything in order apparently. And M sub S can either be a plus 1/2 or a negative 1/2, and that's its only choices. Now, as far as what it means, this is going to be the energy level or shell. This tells us the subshell. This tells us the number of orbitals. And this tells us the electron spin. With L, if L comes out to be equal to 0, it will be an S subshell, always. If L is equal to 1, it will be a P subshell. If L is equal to 2, it will be a D subshell. And if L is equal to 3, it will be an F subshell. Always. That's just what their numbers indicate. Now, for these, the M sub L can be a 0, it will only be 0 if it's an S because of following the formula that we gave. For P, your M sub L will always go from a -1 to 0 to a 1. For D, your M sub L will always equal a -2, a -1, a 0, a 1, or 2. And for F, it will always be a -3, -2, -1, 0, 1, 2, 3. In other words, you have one orbital. For an S, you'll have 3 orbitals. For P, you'll have 5 orbitals. for a D, and you'll have 7 orbitals for an F. Now, when you're looking at an electron configuration, you can literally go through and you could figure out all of the quantum numbers, but the key, this is telling you your N, this is telling you your L. To get your M sub L, you have to remember the equation that I gave you. It's a negative L to a plus L, which is how I got all of these numbers in here. So for a D, I literally would take the numbers it had, which was -2 to 2, and I would label it -2, -1, 0, 1, 2. And then the spin is whether it's up or down. So for instance, if I'm looking at this electron, I would name the N, and I wanted N, L, M sub L, M sub S. The N is 3. The L because of it being a D, the L has to be 2. The M sub L is a 2, and the M sub S, because it's spin up, is a +1/2. Does that answer? I've lost who I was, your question, Jacob. Okay. Let me see. What do we need to know about the importance of ionization energy and electron affinity? Eva, I actually had to cut a couple of things off of the exam, and that is one of the things that did not wind up on the exam. The big thing is I wanted you to know that ionization energy is responsible for forming cations, whereas electron affinity is responsible for forming anions. Madeline, can I go over how many valence electrons are in an element? Okay, so the easiest way is to look at the periodic table and identify where it's at. If it's a main group element, which is group 1, 2, 13 through 18, then it's going to be whatever the last digit of the group number is. For instance, boron is in group 13. Therefore, the last digit is a 3, so it has 3 valence electrons. Iodine is in group 17. The last digit's a 7, so iodine has 7 valence electrons. For your transition metals, let me get back to what I wanted. For your transition metals, the valence electrons will always equal 2. Except for group 6 and 11. And the reason is group 6 and 11 are anomalies. So the valence electrons will equal 1. And the reason transition metals only have 2 is because the S's are higher in energy than, or is a higher energy level than the D, and we fill the S's before we do the D, and so those S's are our valence electrons. But in a anomaly, there's only 1 valence electron in the S because of it being an anomaly. Did that answer your question, Madeline? If it's not valence, it's core, so. Okay. Think I've covered all the questions in the chat to this point, so now I'm just looking for the next questions. We have about 13 more minutes. I hope this is helping, being able to go over all of this. There is no key for the practice exam. Okay, I was asked, can I review the anomalies in ionization energy? Okay, I know what you're asking me. So when we're talking about ionization energy, basically, there is a slight decrease in ionization energy. Well, come on, work for me here. When you move on to a new shell, subshell, or when you have 1 electron over and above a half-filled shell. I think that's what you were asking me about. So when you look at ionization energy, what we see, for instance, is for period 2 is something that would look similar to this. You would have lithium, and then it's going to go up slightly in energy to beryllium, but then we'll have a slight decrease to go to boron, because what we've gone from here, you have 2s2, and now you've added on a P. And then you'll start to see it increase. So it'll go boron to carbon, and then carbon to nitrogen. And then you'll wind up having a slight decrease going to oxygen, because right here, if you look at the 2P, it is half filled. And when you add the oxygen, when you go to oxygen, what you've done is you have messed up a half-filled, whoops, not that much. You've messed up a half-filled orbital, and then it'll continue to grow from there. So oxygen will go to fluorine, which would go to neon. So that's the general trend. So anytime you add a subshell, or anytime you mess up a half-filled subshell, you see this little bit of a dip and then it goes back on. So that's the anomaly in the ionization energy. Did that answer your question, Eva? Okay. Next question is a core electron, everything that is not a valence electron. Mackenzie, that is correct. Basically, you identify your valence electrons, and if it's not valence, then it's a core. We have about 9 more minutes. Any other questions? If you can you go over question 13 from the practice exam? Let's see if I can pull up the practice exam. Because I don't know my questions at all. Let's see. I gave it to you using that one and that. Since my iPad can open it. Question 13. Okay, this is the problem I did previously. What I saw is visible light. I saw 656, and I saw an electronic transition, way to say energy level. So with this particular one, you're going to be using the Rydberg-Balmer. To solve it. Okay. Okay, Jacob says he's having trouble with complete ground state configurations. Okay, so one way you can do this, Jacob, is if you can't use the periodic table, you can use this device. I prefer the periodic table, but you've got to do what you got to do. You get the gist. Basically, I'm just drawing in the SPDFs. And then what it does is you go diagonally through them to get to where you need. So for instance, with silicon, if I did this, it would be 1s, 2s, 2p, or 3s. Let's see, 1s, 2s, or 2p, 3p. Okay, the first thing I would need to know is that silicon is in the 3p's because it's in the third period P subshell or P block on the periodic table. So I'd fill the 1s first, which the max it can have is 2 electrons. Then I would go to the 2s and fill it next. The max an s can have is 2 electrons. Then I'm going to hit the 2p next, and the max electrons a p can have is 6. And then I'd go to the 3s next. The max electrons is 2, and then I'm to the 3p. Well, the 3p silicon is the second element in the 3p, so it'd be 3p2. Is that what you were trying to get at, Jacob? And that would be its state. No worries. Any other questions you want answered on this test while I'm looking at it? Probably can do most of them pretty quick. Number 7. Okay, so when I see zinc and I want to form zinc 2+, I have to remove the valence electrons. You always remove the valence electrons. To form a cation, always. Valence electrons, by definition, are the electrons in the highest shell. Well, the shell is represented by the numerical value preceding it, preceding the letter. So I'm looking for the number that's the highest number. So that would be these. Now you always remove the down arrow was the last one in, so it's the first one out. So this is number 1, and this would be number 2 that I would need to remove. So it's N is 4. Because it is an S, that means that L is 0. The only option for M sub L is 0. And because that was a down arrow, it would be a -1/2. The second electron would be a 4, 0, 0 plus 1/2. Because again, if it's an S, it's 0, which means that its only option for M sub L is 0 as well. Did that answer your question, Mackenzie? Okay. Matt, will there be a lot of questions using Rydberg-Balmer? No, there's only one question. It's very similar in nature to what was on the example test. Okay, number 9. Okay, so this is an isoelectronic series. Because an isoelectronic series means that the number of electrons is the same. And if you look at this, I'm trying to remember what my periodic table. Bromine is element 35. So this has 36 electrons. This has 36. This has 36. This is 36. So they all had 36 electrons. So it's isoelectronic. Anytime you have isoelectronic, a +3 is smaller than a +2, is smaller than a +1, is smaller than a neutral, is smaller than a -1, is smaller than a -2, is smaller than -3. Now the key that we had to do is decreasing size. So we wanted the biggest first. So the biggest first. And then we want to go the opposite direction. We want the smallest last. So the biggest would have been, in this case, the AS3- would have been the biggest, followed by the Br-, followed by the krypton, followed by strontium 2+. Did that answer your question, Mohammed? Okay. And it is 9 o'clock. So it is that time for me to comment. I hope